All right, so in this video, we're going to talk about double integrals over rectangles. Now, before we do that, it's important to go back and review the whole idea of the area under the curve, Calc 1 discussion. So the area was defined to be the definite integral from a to b of f of x dx. And if you remember from Calc 1 how we built all of this up, the dx was the base of the rectangle and the f of x was the height. And so what we were trying to do is find the area of infinitely many rectangles underneath a curve and then sum them all up. And so that was the basic idea of what we started in Calc 1. Now we're going to transition to a volume under a surface. And as we know, many times area is going to be base times height, but then when we compute volume, it's going to be length times width times height. So there's going to be three components multiplied together. And so the dA is going to be for area, and then the z equals f of xy would be that third dimension, or that height, if you will, constructing rectangular prisms underneath the surface. From there, we're going to add up the volume of the infinitely many rectangular prisms, and that is going to give us the true volume by computing this double integral here. Now, that's a difficult picture to draw, so I would encourage you to take a look at your book, specifically on pages 884 and 885. They've got some good pictures in there showing you how these infinitely many rectangular prisms can be constructed to eventually give you the volume under a surface. Now, I'm going to take this a little bit further and specify to find the volume under the surface, let's say z equals f of xy on the region. So that R is going to stand for the region. In this particular section, we're going to be computing double integrals over rectangles. So our region is going to be a rectangular region. And most of the time it's presented in such a way that it might look like this. Let's say A less than equal X less than equal B. And let's say C less than equal Y less than equal D, where A, B, C, and D are constants, and then we have our X and our Y here being defined as independent variables in the function. So what this says is that we've got a double integral. We would place our f of xy in there. So our f of xy, we're computing the volume under the surface on the region. And then we've got some decisions. We can do this one of two ways. We can do this as a dx dy, or we can do this as a dy dx. So that dA is going to be some combination of dy dx or dx dy. The decision is most of the time up to us, especially when we have rectangular regions and these are all constants. We haven't yet computed a double integral yet, but it's very, very straightforward. You're going to start with the inside integral first, and then you'll work your way out. The reason why that's important to mention now is because when we fill in our bounds, the dx being first is going to mean the bounds on the x have to come on that first integral. So this would then need to be an a, and that would need to be a b. Once we have that computed and evaluated, then we would move to the integral with respect to y. Therefore, the c and the d would need to go on the bounds for that second integral. So a c and a d. Similar on the second one that I have up here, we would first compute with respect to y. So this would need to be a c and a d, and then followed by an a and a b by the same logic as above. Now, you might be asking yourself, well, are these the same things? Will you get the same answers? And the answer to this question in this particular case is yes, these are equal. And we're going to be able to use this in many different applications and many different problems throughout this chapter. But this whole idea of these two things being equal and the order, reversing the order, not affecting the outcome when dealing with rectangles, this is called Fubiti's theorem, something that you'll probably see in the homework or even in the textbook when you go ahead and read that. So hopefully that gives you a pretty good idea of how we'll get these things set up. But I want to circle back momentarily before working an example to again kind of remind you what it is we're finding. So let me sketch out here real quick the XY plane. And let's say that we have this right here where we have an A and a B, a C, and a D, which is what I have here. And so X is bounded between A and B, so between A and B on the x-axis. C and D on the y-axis is going to give us this rectangular region that we're talking about. Now, what's going to be kind of hard for me to show on the screen is that above this rectangular region, remember the z-axis, the way I have it drawn, is coming out of the screen at you, so straight up from here. So there's some surface above this rectangular region. The rectangular prisms that I'm talking about are coming out of this region. So maybe I'll sketch these in as a bunch of boxes and picture these being rectangular prisms shooting up. So the volume that we're talking about in this case is going to be the volume that's below the surface that I have here, but above the box that I have right here. And you'll see that more in some of the examples we look at. But for right now, we're sticking to these rectangular regions, and we'll keep things pretty basic for the most part. All right, so the first example we're going to look at here is just going to be us evaluating this integral. And remember how I said you can reverse the order dy dx when these are constants? You certainly can. We're not going to in this case, but you certainly can. But I just want you to start thinking that whenever you're going to start evaluating an integral, you're going to start with the inside, and you're going to integrate with respect to whatever this variable is, in this case x. So your decision on whether or not to proceed directly as given or to interchange is going to sometimes be dependent upon how easy is the integration with respect to the variable you're starting with. But again, in this case, it's not very difficult, so we're just going to start with dx. Now, we're going to integrate with respect to x, meaning that anything that has a y in it is going to be treated as a constant. So when I integrate a constant with respect to x, that's going to give me my x e to the y. All right? And then when I integrate this with respect to x, that's going to give me a negative cosine. And this is going to now be evaluated where x equals 0 and x equals pi over 2. Now, you don't always have to write x equals here, but because there's multiple variables, to avoid confusion, I know that I'm only going to plug the 0 and the pi over 2 in for the x's. So this isn't a bad habit to get yourself into if necessary. And then I'll put my dy out there. Again, I'm only plugging the pi over 2 and the 0 in for the x's. So that's going to be a pi over 2 e to the y minus, when I plug a pi over 2 in here, I get a 0. Then we'll have minus, and then a 0 minus 1 dy. So when I plug the 0 in, that zeroes that out. When I plug the 0 in, that gives me the 1. So now let me just clean this up a little bit here. We'll go from 0 to 1, pi over 2 e to the y, and then that'll be a plus 1 dy. So I've completed the first one. Now I'm ready just to move on to the second one with respect to y, of course. And so we'll have a pi over 2 e to the y plus y, evaluated from 0 to 1. So when I plug those in, you can see how it's going to fall apart pretty fast. Pi over 2 times e plus 1 minus pi over 2. That minus pi over 2 comes from when I plug this in right here. E to the 0 gives me a 1. So that would be the final answer. So what we found is the volume under the surface on this rectangular interval right here. And you could certainly draw the rectangular interval if you wanted to. I doubt you'll get a whole lot from it, especially not really understanding what this looks like without a computer. But regardless, that's the number that we found. All right, so for this example, again, we're just going to get a little practice in dealing with these multiple integrals. So nothing really special about this one other than we're going to go ahead now and integrate first with respect to y. So that means we're going to treat all of the x's as constants. So my integral, if from 1 to 2. And then treating this as a constant, and this is my variable, remember that's going to be that natural log of the absolute value of y. So x, natural log absolute value of y. And then for the second term, this is my variable, and the 1 over x out in front is a constant. So when you integrate that, that's going to be the whole add 1 and divide. It's going to give us a y squared over 2 times x. And this is now where we're evaluating at y equals 1 to y equals 3. And so I like putting the y equals there, so I remember to only plug them in for the y's, not the x's. And then we'll have our dx. So going from 1 to 2, when I plug the numbers in accordingly, I'll get an x natural log 3 plus 9 over 2x minus, now I'm ready to plug the 1 in. That'll give me a 0 because the natural log of 1 is 0, plus 1 over 2x. And I still have my dx out there. Let me clean this up just a little bit. And I'm going to write this as natural log 3 times x. Not that it really matters, but when I'm about to integrate here, this is a constant out in front, so it might make it a little easier to look at. And then when all is said and done on this back side here, this is going to give us a plus 4 over x dx. So now I'm ready to integrate with respect to x. For the first term, it's another add 1 and divide. So natural log 3 over 2 x squared. And then here we have another natural log absolute value of x hanging out there. So we'll take that from 1 to 2. And as I plug this stuff in, I'll get a 2 natural log 3 plus 4 natural log 2 minus, now I'm ready to plug the 1 in there and there. That'll give me a natural log 3 over 2 plus 0. And then to clean it up, we'll say 3 over 2 natural log 3 plus 4 natural log 2. And you can certainly do a variety of things with that in your final answer, but this is where we'll stop on this one. But hopefully, again, you guys are starting to see that the double integrals really, to compute them, aren't very difficult. You're just going nice and slow, making sure you're not mistakenly thinking one thing's a constant when it should be a variable or vice versa. But beyond that, it's really just a matter of doing the same thing from Calc 1 twice.